Okay. So here our friend John Carlos Baez has a diagram of what's going on.
All right.
So first, this picture is showing very roughly what things look like from just looking at the cube straight on. So what are you measuring the distance?
Okay.
And I don't think we can stop this, but you can see that in the beginning, at even a quarter of the speed of light, it's not that big of a shift. Even at half, we found it was about a 15% contraction.
But yeah, it starts to get near the end.
Yeah.
It just contracts a lot.
Yeah. So it moves very quickly, or slowly in the beginning, and then very quickly as you get up to
the last 10% maybe?
Yeah, it shrinks really fast. But over here is the visual appearance. And what do you notice is happening here?
Oh, the cube is turning at first, and then it looks like this side is actually bending. That side's going up. And this side over here was bent, actually.
So here's a pencil. You can point at the screen. What do you see bending?
So it looks like this back edge here is bending.
Huh.
Here you can see it really well, and then that face is slanting up, even though it's supposed to have all right angles as when two edges meet.
Yeah. So it's weird that this is bending, and apparently in his tweet above this says this effect is called the Penrose-Terrell rotation because it was discovered by Anton Lampa in 1924, but nobody paid attention until Penrose and Terrell each rediscovered it independently in 1959. So I'm going to ask you, what do you think makes the cube appear to rotate? What do you think is causing that to happen?
Well, are we assuming the cube stays in like the same orientation?
Yep, that's right. It definitely, we are absolutely assuming that the cube stays in the same orientation, that it stays with its face just pointing straight at you the whole time. The cube.
Well, right here, because it's shrinking, maybe we can start to see that face shrinks, and maybe it's just like perspective that causes it to shrink. You can see the face is shrinking in. And so maybe that's what's causing it to appear to rotate, but in reality it's just that one face is shrinking.
Okay, so maybe the shrinking has something to do with it. The other piece of the puzzle, and this is something that we're just not used to seeing in our normal everyday life, is that in our normal everyday life it seems like the speed of light is infinite, right?
Yeah.
If we look at a light on in the kitchen, we don't think about how long it takes the light to get to us.
Yeah.
But if a cube is whizzing by at nearly the speed of light, then suddenly it starts mattering how long it takes the light leaving this corner to get to the front of the cube compared to how it gets to the front our eye. Like it might take as long to pass the length. Like if we're one cube length away,
yeah,
it takes as long for the light to go from the back corner to the front corner as it does to go from the front corner to our eye. But when the cube's moving at nearly the speed of light, the cube itself has moved during that time period.
Yeah.
And so that's
what
another contribution to the rotation. But John's friend Greg Egan actually did an even different simulation, sorry, is the word I'm looking for. And this shows the difference between Einstein's relativity theory and what Galileo and Newton would have said it looks like.
Interesting.
So you can see Galileo and Newton, first of all, the speed can go above the speed of light.
Yeah.
Secondly, Galileo and Newton wouldn't have thought that the cube was shrinking. They didn't know about that shrinking due to speed, but they still would have seen some of the rotation.
Yeah.
And in fact, the Galilean slash Newton ideas are so strange because they're not what people are used to who work in physics. He actually turned out didn't do this quite right the first time, and it's even weirder. So we go down to here. Here's in the Galilean Newton case, what you would actually see. The cube rotates and rotates and rotates, and then all of a sudden it comes in from the other side at the same time. And then you get a sort of a double image of the cube.
That's weird.
When you're above the speed of light. What do you think? Why do you think that would happen, where you would see the cube actually twice if it was going faster than the speed of light?
Well, I assume maybe at the speed of light you would see just them touching, maybe?
Yeah, maybe that's when they touch. But later on you actually see two images of the face.
Well, one image might be the image where when you first see the cube, and then like when you first see the cube coming, and then you see that, and then by the time the light has reached your eyes, the cube's moved.
Yeah.
And so when that light comes to your eyes, and that's kind of what you see.
Yeah, so you're definitely on the right track. If the cube is moving faster than the speed of light, so when the cube is maybe over here, if you think about the triangle between your eyes, the cube, and then like where it's closest to you,
Alright.
it emits some light here. But that light has to go a little bit farther than when it's here.
Yep. And so they would both reach your eyes at the same time.
They would both reach your eyes at the same time, and so you would see two cubes kind of blended together.
Yeah, it's cool.
Yeah, it is pretty cool. But the amazing thing is that doesn't happen. What actually happens is what Einstein predicted. So the cube shrinks and bends, and you don't end up, you can't, in Einstein's theory, ever cross the speed of light.
Yeah.
So you never see the double cube.
It's cool.
Yeah, that is pretty cool. All right, hey, good job this morning, huh?